So we know about vectors. We have a way of adding them, subtracting them, and we have a kind of multiplication. We can take a scalar times a vector. So we have that kind of multiplication. The result is another vector. Scalar, remember, was a real number. It just stretches the vector or contracts it or flips it if the scalar is a negative number. So today we want to talk about another kind of product. There are going to be two, actually. We'll talk about the dot product, and then later on we'll talk about the cross product. So the dot product is very closely related to matrix multiplication, which we've already discussed. If we look at a vector, say this vector u that consists of the numbers 2, -4, and 5, if we think about the comma as meaning over, then we could take that vector and we would write it as a matrix this way. So 2 over -4 over 5. So in this class, whenever we see a comma, we can treat it as though it means over, and that will turn this vector into a matrix. So if we have another vector, maybe this vector v, which consists of 1, 3, and -2, then it's also a matrix, just sort of a column here, 1, 3, -2. So when we talk about vector, usually we mean column vector, although we could transpose a vector, so we could switch the rows and columns. In other words, we'll denote that by putting a little t on there. To transpose a matrix means to take each column and make it a row. So the first column becomes the first row, and so on. So, all right, by the same token, I guess U transpose would be this matrix that consists of a single row, 2, -4, and 5. And here's our idea. If vectors are actually matrices, notice these two matrices couldn't be multiplied because the dimensions are wrong. Remember that in order to multiply two matrices, the number of columns in the first has to match the number of rows in the second. But we could do this. We could take U transpose times V, or we could take V transpose times U. Then the dimensions will work out. See, U transpose is 2, -4, 5, and V is this matrix 1, 3, -2. Remember, for matrix multiplication, this is perfect because you can multiply the first entries, the second entries, and the third entries. Let's see what we get. 2 times 1 minus 4 times 3 minus 5 times 2. I'm just multiplying corresponding entries in these two, just like we did when we were multiplying matrices. 2 minus 12 minus 10. We get 2 minus 12 would be -10, minus another 10 is -20 for the answer. This is what we're going to call the dot product. So the dot product, when we write U dotted with V, what we mean is to take U transpose V. What actually happens is the first entry of U multiplies the first entry of V, the second entry of U multiplies the second entry of V, and the third entries multiply, and then we add them all up. So because the result is always going to be a single number, sometimes we call it the scalar dot product. So we call U dot V the dot product, or because the result is a single number, a scalar, we call it the scalar dot product. But if we just say dot product, you know what we mean. And notice it doesn't matter which way you dot them. If you take V dotted with U, that would technically mean taking V transpose times U, which would be this matrix 1, 3, -2 times U, which was 2, -4, 5. Can you see you're going to get the same product? Because you get 1 times 2, right, the product of the first entries, minus 3 times 4, the product of the second entries, minus 2 times 5. You're multiplying the same numbers, you're just doing it in a different order. You're adding them all up, you're still going to get the same answer. It's still 2 minus 12 minus 10 is -20. So that's always true, that the dot product is commutative. When we look at the cross product, that won't be true. We'll actually get a slightly different answer if we multiply in a different order.